More students coming in. And notes. These are the notes. Let's see. Someone we curve the exam. Yes, I do. Not the exam. I curve the final grade. Okay, so I calculate the final grade at the end of the semester, and then I curve that final grade. Okay. And okay, yeah. So we're doing 2D relative velocity. Okay, we did a very simple case of the relative velocity, and now we're going to do a more difficult case of the relative velocity. Insert here, page break. Today is October 07, 24, Monday. And going back to the syllabus, right? So here you go, I'm gonna put it here, 3 and 4, and now it's going to be version 5 of the syllabus. Three and 4 to the motion 3, laws of motion. Another student coming in, Real Williams. Okay. And I'm gonna get some other things here. Factors to the motion genetic. Let's see. Let's see if we have. Yeah, okay, we covered that. We don't have what I want. Let's see if we have it what I want here. Yeah, okay. Yeah, we're doing the 2D show here. And this thing, and I want also to show you where we are in the book. So you have an idea. Your Wiley Plus. When we start to trying to come in. Let's take a look here at the book. More students coming in. Okay. The next exam is going to be on the end of the month. Okay. And at the end of the month, also the 2D motion is going to be due. Homework for 2D motion is due as well. Homework 3 and 4. Okay. Even though this homework here showed up in the first exam, I'm giving you a little bit more of time, right, to do it because it came late in the later compared to the other two homeworks. Okay, now let's take a look here at this book. Launch more students. Okay, kinematics in 2D. projectile motion, relative velocity. So that's the last thing that we are going to cover in chapter 3. Okay, so let's write it down in the notes here. We are covering. We covered the following material in chapter 3. 3.1, displacement, velocity, and acceleration vectors, right? In 2D. That's what this chapter is all about. The next one, 3.2, equations of kinematics in 2D. Take a look here. Okay, here is one example of the equations in kinematics when you combine motion along the x and y axis. Okay, and then the next one was the projectile motion, 3-3, projectile motion, which is a very important type of motion that can be applied to cannoneers. For instance, if you're going to fire a cannon towards your enemy, right, you have to know the equations of motion of your cannonball. And that was the struggle that the cannoneers at the time of Galileo, the 1500s, 1400s, right, that they were having. How can I fire my cannon properly to reach my enemy ship, for instance, or my enemy troops, right? Those equations of motion give them a better, an idea of how the cannon can be aimed. And 3-4 is 3.4. 3.4, relative velocity. Okay, that's what we are covering right now. I'm going to boldface everything just to emphasize that we managed to cover that. Okay, in the previous class, what did we do? We did the following. Okay, 1. So 1, we did a very simple example of relative motion in 1D, in 1 dimension. Okay, this problem was so simple. This example was so simple that we did not need the formal equation of relative velocity. Okay, and then what else did we do? And then after doing this example, come on, I derived the genetic equation for relative motion, right? And we did something else. Use the equation of relative motion. Don't forget the vectorial equation, right? Of relative motion to solve the example we did in item 1, right? So we did the example in here In item 1, we didn't use any formal equation. We just analyzed our drawing, see how the two different referentials were moving. And from there, we could figure out what would be the relative velocity of one object with respect to the two different referentials, okay? And here we repeat the problem, but we repeat the problem in a formal way. We repeat the problem using the equation derived in item 2. That's what we did, okay? And now we will solve a more difficult problem. It's a more difficult example, right? In 2D, in 2 dimensions, using the vectorial equation of relative motion. That's what we're going to do. And this is don't underestimate the power of this equation, okay? And don't underestimate the power of this equation. Okay. It is very important. This equation is very important. It's very important for navigation. Very important for navigation, okay? No matter if you are Christopher Columbus sailing from Spain to the Americas, or if you are a commander of a jetliner, you have to know this idea of relative motion to reach your destination in a faster way, in the best possible way. As an airplane pilot, when I was flying, I was trained as an airplane pilot, and when I was flying up there, I needed to know the direction of my wind to reach my destination properly. Okay, and even for landing, you have to know the direction of the wind so you can safely land my airplane in the airport. Okay, and in order to do that, you have to know those equations of relative motion. And let's take a look at it's not difficult to memorize this equation of relative motion. It's not difficult. Okay, I already provided you a very simple mnemonic way of doing that, right? So here you go. Suppose that you have the velocity of a point P with respect to a referential B. Okay, consider 2 referentials, right? One referential A, another referential B. And let me show you I'm gonna close this one here. Yeah, let me show you the drawing, the illustrations here so you can understand better. Here. So, okay, so here you go. You have 2 referentials, A and B, and I'm going to make it less busy so it's easier for you to see, right? First, I'm going to start just with the referentials A and referential B. Referential A, referential B. I'm going to erase this guy here so it's not too busy, right? Let's see. We start with this drawing here, referential A. Even better, I'm going to simplify even more. I'm going to just show initially just referential A and then just referential B. Okay. Here you go. Consider referential A. right? And then we also have referential B. Referential A has X and Y axis. Referential B has X prime, Y prime axis. Okay. I also illustrate those referentials in different colors. And then we have to also have a point P. Okay? And this point P, referential B, first referential B is moving with a velocity relative to referential A, right? Referential A and B can be, for instance, a pedestrian in the freeway at rest in the freeway, or a car at rest in the freeway, okay? And referential B can be a second car that's moving in the freeway, okay? And B and point P can be, for instance, another car that's moving in the freeway, okay? So we can, just to have a good, for understanding purposes, right? It's always good to give an example, real life example, so you can understand what the A, B, and P stands for. So let's say a referential B, A is the ground, okay? Someone is standing there in the ground, is at rest with respect to the ground. Referential B can be, for instance, a car number 1, right? Which is moving with respect to the ground. Car number 1. And point P can be a car number 2 that's moving with respect to the freeway. Car number 2, for instance. But you can make it as generic as possible. It doesn't have to be a car, doesn't have to be can be an airplane, can be a train, okay? And so on. So now, what else do we, and I'm going to erase here and just leave in a generic fashion. Point P, referential A, referential B, okay? Referential B. Another example, referential A, here you go. Yeah, can be the ground again, but now referential B can be the water in a river that's flowing with a given velocity, okay? Water in a river. And let's see, point P can be, for instance, a boat in the river. Different examples of how those equations can be applied, right? And then just going back to our generic notation. Now I'm going to put a vector velocity here in this particle. Let's say velocity of point P with respect to referential A, for instance, right? That's what I did here in this illustration. Okay, those are the velocities of the referential, and this velocity for referential B doesn't have to be along the x-axis; can be in any direction as well. Okay. Having said that, now that we have all the notation, right, that we need, so I have right in here a relationship between those velocities. Suppose that here is just the velocity of point P with respect to referential A, right? But let me just make it change this notation. Let's say this velocity is the velocity with respect to referential point P with respect to referential B, right? So we know those two velocities. We want to find the velocity with respect to referential A. That would be the equation that we have to use. Okay? So if you know VPB and VBA, if you know VPB and VBA, and want to find VPA, you must use the following equation. Okay? You go. Now, so here you go. Again, I'm going to repeat how you can easily memorize this equation, right? If you want to know velocity of P with respect to A, it is going always to be a summation between two velocity vectors, okay? And the first velocity vector is going to have the point P at the beginning, velocity of point P, and the second velocity vector will have the velocity with respect to referential A, right? First and last, first and last. And then what goes in between is going to be the referential B. Okay? And this applies also if you want to find out the opposite. Suppose that you want to find the velocity with respect to referential A. Velocity of P with respect to referential A, right? Let's see. No, I'm sorry. Suppose that you want to find the velocity of point. What's going on here? Okay, I have to erase this one first. Okay. Suppose that you want to find the velocity of point P with respect to let's see. If you know VPA, right? And VBA, and want to find the velocity of point P with respect to B, referential B, here you go. You must use which equation? Okay, you must use the following equation. I'm going to copy this one here. Place right in here. Remember, first and last, right? First on the left side is going to be point P. Last on the right side is going to be referential B. Okay. And then look what we have here. We have to put referential A here, which has a color green. And referential A, velocity of referential A with respect to B, right? Notice that here we have the opposite, right? Velocity of referential B with respect to A. And those two velocities here with respect to each other referentials also has a very simple relationship where you go. There's a very simple relationship between them. And that is the relationship. I'm gonna get there. A with B, B with A. Here you go. With a minus sign. Okay? With a minus sign. That's the relationship between the velocity of those two referentials. Okay? Okay, so what I'm going to do here, let's see if I can find I have an example here, very nice example in terms of a boat. Let's see if I can find here in my notes, okay? I'm gonna pause momentarily my recording. recording. Good. Chapter 3. And, the situation is the following. To the motion, I'm going to copy. Okay, so we have referentials A and B now. Okay? In the case of referential A is the ground, right? Is the ground, and B is the water current in a river. Okay? The water current in a river is moving at 3 meters per second. And the velocity of point P with respect to the margin of the river, with respect to the ground of the river, is 4 meters per second. 4 meters per second north. Okay? 4 meters. Notice that I put X. Here goes X axis. I'm going to put Y axis here. This other one is going to be X prime axis. And the other one is going to be Y prime axis. Okay. What we want to know, we want to find out the velocity of point P with respect to referential B. Okay? With respect to this water current. Just, so what we do, go back to our, so consider a very simple example. Look at the example 10 of the book, which is similar to what I'm doing here. It's not exactly equal, but it's similar to what I'm doing here. Okay? Consider a river with water current. The margin equal with a water current. I'm going to put here between parentheses referential B. The margin of the river, referential A, and a boat that would be, point P. Okay? So suppose you manage to cross the river with a vector velocity VPA that is perpendicular to the margins of the river, right? Let's see, consider one. I'm going to put something else here. You know VPA and VBA. Okay, let's put it this way. Suppose you manage to cross the river. You managed to cross the river with a velocity vector VPA that's perpendicular to the margins of the river. Just like we have right here. It's not easy to cross a river with a velocity vector in which you have this velocity vector pointing perpendicular, right? Because you have this water current that's going to drag you along the way, okay? It's not easy. So the question here, find VPB, which is the velocity of the boat with respect to the water current. Okay, look at example. Let's put example 1, RV. RV stands for relative velocity. Okay, so solution, how you have to do is to use this equation here, right? Velocity of the boat with respect to the water current is going to be the velocity of the boat with respect to the margins of the river plus velocity of the margin of the river with respect to referential B. Okay, so here we go. Going back to my illustration here, I do not have VA of B. I have only VB of A, which I know is from the left to the right. But I know that there is a relationship between VBA of A and VA of B, right? Recall that we do not have, here you go, let's write it down. We do not have VA, velocity of the margin of the river with respect to the water current of the river. But we do have VBA. We do have VBA, right? And on the top of that, there is a relationship between these two vectors, which is given by, right? Just one is the opposite of the other. Here you go. One is just the opposite of the other. So we proceed to solve this problem. Right? Here you go. Write down everything in terms of the known parameters. Substitute VA of B, VA with respect to B, by this other one, right? That would be the final solution of my problem. But now let's come up with a graphical way, right, of visualizing this velocity vector, right? So this one, okay, this one right here. It's right in here. VP of B is going to be VP of A minus VB of A, right? If this one here is VB of A, let's put it right here. This one here must be VB minus VB of A. And that would be the relative velocity vector that the water current will see your boat displacing, right? It makes sense, right? Because if you are moving along with the water current, let's say, suppose that you have a second boat that you're moving and you're moving along the river, downstream the river, with the same velocity of the water current, and you look at this other boat here, you're going to see this boat moving away from you, moving towards the left side of the river, right? And that's exactly what this vector velocity is showing, right? At a given instant of time, this boat is going to be here. A little bit later, this boat is going to be a little bit higher, right? Right in here. I'm gonna take away this guy. So, oh, no, we're gonna leave it here. But what's gonna happen to this differential? This differential here is going to, a little bit later, is going to be a little bit further downstream, right? Okay, a little bit later, so this guy actually seeing, having the impression, right, that this boat is moving to the left according to his differential. a little bit later, okay? Get everything here. A little bit more. Okay, will be like that. Initially, going back to our drawings. Okay. Initially, that was the velocity vector that it had for the point. That would be v. I'm gonna put it right in here. I'm gonna use this one here. V. That's gonna be r. I'm gonna put r. R of p with respect to b. Right. I'm gonna erase this one. Right. A little bit later, the vector position is going to be different because both the referential and the bolt are moving with respect to each other. Okay. A little bit later, they're going to be even further apart. Okay. So when you take delta r over delta p, right, you are going to get a velocity vector that's going to be somewhat like that. Let's see if we really get that, right? Here you go. And I'm going to even do the following. Let's see. Yeah, I have to distinguish those position vectors, right? RPB. One. Next one is going to be RPB, comma 2. The next one is going to be RPB, comma 3. They're different vector positions. If I want to know the velocity vector with respect to referential B, what I have to do? I have to do delta RPB over delta T, right? So let's get just those two vectors first. I'm going to copy and paste. I'm going to need only this vector position. I'm going to leave this one right here for comparison purposes, right? Simplify, okay? And I'm going to get the RPB2. RPB2 is like that. RPB2, right? And then if you get the subtraction of those two vectors, you're going to get this genetic direction, all right? Let's see. Don't forget, it's RPB3 minus RPB2, right? We will not get RPB3 minus RPB2. So RPB2 has to change direction because we are going to get its negative. This one here, okay? That's very lousy record. arrow here. I'm gonna try to get a better arrow. Let's see this one. Okay, better, right? Now I'm gonna change the arrow here as well. This one, this one? No, it's not this one, it's all the way around. It's this one here that I want, okay? And look what we get for the RPB3 minus RPB2. We get a resulting vector that is in the same direction as this vector here, right? Sideways to the left. Right, so here we go. It's going to be resulting vector. Just by doing this nice drawing, notice that, what I did here, I basically played a movie, right, with you, right? So let's go back here. Here's the one-dimensional case, right, that we did before last time. This is still the one-dimensional case. Now we are doing a more complicated problem. We're doing a two-dimensional case. We have referentials A and B, okay? The particle is right in here at this position. The boat is right in here at this position. And the water current is at a given instant of time at this position, okay? That's going to be, I'm going to put a different color. That's going to be the vector position of your boat with respect to referential B, the first vector position, okay? Next, a little bit later, the water current moved a little bit to the right and the boat moved upwards. And now we have a different vector position, which I'm going to put with a red color just like before. Okay? And then further down, after a little bit later on, right? Further down in time, right? Or a little bit later on, this referential is going to move further to the right, and this boat is going to move closer to the other margin of the river. That was going to be my other vector position with respect to the water current of the river. When I get the delta R between those two positions here, we end up getting a resulting displacement vector that points in the same direction as this other vector here that you see, the velocity vector, right? Recall that the velocity vector is parallel to the displacement vector. So the genetic direction of my resulting displacement vector is in the same direction as the direction of my velocity vector. That's one example. Now let's take a look at another example. Okay. And now instead of, it's going to be this one here, right in here. Okay, now copy, let's see, this one. I have to copy those three here. Let's see, what time is that? Oh, I think before we go to the second example, let's take a little break. Okay, illustration here and roster. Lecture. Today is the 7th of October. I am, yeah, already here. So Audrey Aguilar, are you there, Audrey? Hello, Audrey, are you there? I can see Audrey there, but I don't hear from Audrey. Matthew, are you there?
I'm here, Professor.
Thank you. Brianna Carrillo. Okay, thank you, Brianna. Oh, okay, thank you, Audrey. Okay, let's see. Audrey is here. Brianna is also here. Jazzy Castellano. Thank you, Jazzy. And Gabriel Contreras.
Here.
Thank you, Gabriel. Liliana Cortez. Liliana is here. I don't see Liliana in my list. Okay. Next is Juan Escalera. Let's see where one's not here. Molly.
I'm here.
Thank you. Henry Kim. Hello, Henry, are you there? Okay, could I start here his name? Ruth. I see Bruce as well, but I don't hear from her. Next is Noemi Martinez. Okay, hi Noemi, thank you. Next is Danae Miller. I cannot hear you, Danae. You might want to type there in the. Okay, thank you. For some reason, why is that? I cannot hear. Let's see, maybe my mic. Yeah, it's not my speaker because I heard other students, right? Ramon Olivares.
Here, Professor.
Thank you. Next is Taylor Thorne.
I'm here.
Thank you. Next is Alexis. Alexis, it's no longer. You drop the course. Let's put it here. Okay, and Stephanie Ramos.
I'm here, Professor.
Thank you. Next is Jeremiah Reyes. Hello, Jeremiah. Henry replied. Okay, Jeremiah, I don't hear from Jeremiah. Let's put a star here. Sean Rosario.
Here.
Thank you. Ali Standard.
Here.
Thank you, Ali. Jason Strait.
Here.
Thank you. Elena Trujillo. Hello, Elena. Okay, I'm going to put a star here in Elena's name. Next is Jason Valadares.
Here.
Next is Stephen Vathapali. Thank you. L'Oreal Williams. Next is Nuhamin 1. I don't see Nuhamin here. Yep, I don't see it. Aliyah Zavala. Thank you. And let's see how many students we have. Let's see. 949. Ruth, are you there, Ruth? One more. Okay, thank you. Jeremiah, raise. One more chance, Jeremiah. Okay, and Elena Trujillo, are you there? I have 22 students. Yeah, 20 plus 2. Okay, good. So it's 9:50 now. Let's go have our break. Break from 9:50 a.m. to 10:05 a.m. Okay. So I see you in 15 minutes. Chegou já? Okay, I want you now to understand exactly what everything here means, right? What all that stuff means, okay? When we are talking about vector velocity of the boat with respect to this referential A, right? It means, what does it mean? It means that the displacement of the displacement vector of the boat is going to be also perpendicular to the margins of the river. Okay, that's what it means. And it's very important to understand this distinction here. Here you go. I can write it down. VPA. Very important to understand this distinction. Okay, good. I discover. Okay, good. Delta R. See, delta R of P with respect to A, right? I'm not gonna put this 4 meters per second. That's what it means. So the boat is taking the shortest route. Here you go. Here's one margin. Here, let's say the other margin is right in here. I'm gonna put the other margin. And I'm gonna take away this arrow. Okay? The other opposite margin. So note see that in this specific case, the boat is taking the shortest route to get there on to the other side. Okay? Okay. And then, but then you have to look at this other vector here, right? That's your VPA. And here you go. That's your VPA. And I'm going to do something else here. And no, not this one. Not this one here. Let's see. Ooh. Yeah, here you go. Parallel. Gosh, that's terrible. Okay, I'm not gonna do it. Why there's a prime there? This prime is not supposed to be here. Oh gosh. Let's try. Vector, yeah, good. V, E, A, okay? Like that. Let's not forget, this vector here is parallel to this other vector here, right? VPA is parallel to delta RPA. Okay? Now, let's take a look what this other vector here means, okay? That's very important. That's a very important piece of information that people, instructors of physics, they usually don't know and they don't tell the students, okay? Okay, this other vector that you see here is a vector that's showing the direction where you must point towards, where you must point your boat, okay? So that was this. So if I were to draw my boat, I'm gonna draw my boat right here. Here is my boat, right? Made up a rectangle and a triangle, okay? That's my boat. Let's make it very bigger like that. No fill, and I'm going to outline it with black. Here you go, like that. I'm gonna do the same here with this. And I'm going to group. No. I cannot do that. Why it doesn't do it? Let's try it again. This one from scratch. Good. And now I'm gonna get my triangle here. The nose of the boat, right? Shrink a little bit here. And put it fill with white. Like that. Okay, now I should be able to get what I want to do. Yep. See that? Didn't do grouping before. Okay. Don't forget. So what this VPB vector means here, okay? In this case, this VPB vector means what? Means the attitude of the boat. In order for the boat to cross the river in a straight line, the shortest possible way, it must be pointing towards this direction that you see, okay? Very important. So the boat points sideways to make up for the drag of the river that's trying to drag it to the right. And by pointing to the left, it will be cancelled. There will be a vector velocity component of the boat in the left direction here that's going to cancel the water current, the velocity of the water current, okay? So if you want to cross the river along the shortest possible direction, you have to point the boat away from the current. Okay? That's very important. VPB is also the direction along which the axis of the boat must point. Okay, very important. And that happens to airplanes too, okay? If you're flying an airplane, and especially if you want to land in the runway and you have a crosswind, you gotta point the nose of the airplane into the wind while you describe a path that's parallel to the runway on the ground, okay? So that's important thing to keep in mind. Okay, and now we are ready to do, let's write that down here. Okay, so I'm gonna make a slightly simpler drawing so I can I can cut and paste into my notes. Here you go. Margin, lower margin, upper margin of the river. Okay, that's the displacement vector that's parallel to the velocity vector of the boat with respect to the referential A. Okay, and I will copy that. And paste right here. Okay. I'm going to write that down. In the above figure, comma, vector VP of A is parallel to the displacement vector delta R delta R of P with respect to A. This means that the boat is crossing the river along the shortest possible path, not necessarily the fastest possible path, okay? Not necessarily the fastest possible path. This means that the path along the river will be the path of the boat, right? The path of the boat along the river will be perpendicular to the margins. Okay? Perpendicular to the margins. One more thing that's very important. That is very important. The vector VP of B, okay? The vector velocity VP of B in addition of being the vector velocity of the boat with respect to referential B that's moving along the river is also the vector velocity P of B is also the direction that the longitudinal axis of the boat points, okay? Assuming that the, I'm not going to complicate that one, okay? It's also the direction of the longitudinal axis of the boat. Longitudinal axis of the boat. This direction we also call the attitude of the boat. Okay? The attitude of the boat. And also the attitude of the airplane. If you have been to the beach, you have, hopefully you have seen something like that, okay? If you have been at the beach, let me illustrate another example of this velocity vector and the attitude that's involved, okay? Next time you go to the beach, here you go. Next time you go to the beach, okay? Watch, for instance, the seagulls flying along the shore, right? Along the shore. Have you ever noticed that? Especially in days when the sea breeze is very strong. Breeze, right? It's very strong. What will you see? What will you see? Okay? You will see that the seagulls that although the seagulls are flying, the path, right? Although the path of the seagulls along the seashore is parallel, they are trapped into the wind, okay? They are trapped, just like this boat is trapped into the current, okay? So the drawing is something like that. Here's the seashore, okay? The wind is blowing from the sea. Velocity, I can even, here you go. I can even say that velocity of B with respect to A. I'm going to need this one here. Yeah, here you go. Let's do this way. Here you go. $24. This is kind of a concept, a little bit difficult to understand, okay? That's why, and that's the differential of A, right? And then I'm going to put here differential of B, a smaller axis. And I'm going to put it a different color now, so you can easily distinguish referential B from referential A. And then I gotta put the X prime here. That's gonna be Y prime. Okay, and I put it right in here. That's the direction of the vector of B. I'm gonna put it A. This one is A. The other one is B. okay? Differential B, seashore, and vector velocity of B with respect to A. See if I can get it red color. Yeah, red color. This one is going to be red as well. Okay. Vector velocity of B with respect to A. And now I'm going to draw this seagull as a cross. Okay. Illustrate my seagulls. Let's see if we have a cross here. Yeah, we have a cross. Let's see if this one works the way I want. No, I don't like that. Yeah, I don't like that. I want to make my own cross here. Here you go. Here's my seagull, okay? The longitudinal axis of the body of the seagull. Make it a little bit thicker. And the wings of the seagull. Okay, here you go. The wings of the seagull. If the seagull keep this attitude, okay? If the seagull keeps this attitude, what's gonna happen to the seagull? At a given instant of time, it's gonna be here. A little bit later, it's gonna be blown out of the course. A little bit later, it's gonna be blown, continue to be blown out of the course, see that? And the displacement vector of the seagull is gonna be something like that, okay? Let me put it in the right position, okay? That would be the displacement vector of the seagull. Do you agree with me? Okay. The wind is blowing the seagull away from its course. And I'm gonna make it thicker. See here. Arrows, arrows, arrows. Like that. And that would be what? That would be delta R. The seagull, I am denoting it by the point P with respect to A, okay? That would be, however, seagulls are smart creatures, okay? So, and they like to fly along the shore. So if they want to fly along the shore, what do they have to do? Well, group it here. They have to crab into the wind, okay? If the velocity of the wind does not change, what's going on here? Okay, if the velocity of the wind doesn't change, the seagull will be able to keep its displacement vector parallel to the seashore. Like that. It's the same thing for the boat, okay? And I'm gonna put it the same color. Yeah, like right, like that. And in the previous one, okay, well, I put it blue as well, right? Okay, so we can write it down. I'm gonna copy that. Okay, so in the case of a seagull that's flying along the shore, comma, if it, right, does not adjust for the wind, for the sea breeze, right? For the sea breeze that's blowing from the ocean, comma, it will be blown off course according to the figure below. Okay. Seagull represented by the cross blown out of course by the wind, right? Longitudinal axis of the seagull. Longitudinal axis of the seagull is parallel to the seashore. And then we have that other case. Go. Okay. Okay, almost the same thing, but it's slightly different. Okay, it's smarter seagull. Smarter seagull represented by the cross. Grabbed by the cross, grabbed into the wind. In this case, he flies parallel to the seashore because he adjusted its attitude towards the wind. Okay? And it's all in those equations. I like to tell my students that those seagulls, they're smart. They know about relative motion. That's why they adjust their vector velocity in such a way to fly parallel to the shore. Okay? In both cases, in the above figures, A represents the referential of the shore in the above figures. B, the referential attached to the air mass is like wind. Okay, and right, B. Okay, and the cross represents the seagull flying parallel to the shore. A represents the differential of the shore, B the differential attached to the air mass, wind, dB of A. dB of A represents the vector velocity of the wind with respect to the shore, right? And the cross represents the seagull flying parallel to the shore, but grabbed into the wind. Okay. Third break. Okay, so that's what I want to cover for you. And then at the end, all you have to do is to do this, all you have to do to find out the speed, right? The final speed of the boat or the final speed of the seagull. All you have to do is to take the magnitude of this vector. Okay, any questions? I think it's a good thing to cover, something like that, because it has practical applications. We do not have this problem with cars because cars are they have tires, right? That ensure that your attitude remains the same with respect to the axis of the freeway. But in the case of a seagull, of an airplane, they don't have contact with the ground. They're just flying there in the air. And their ground path, the path along the ground of the seagull of the airplane ends up being affected by the wind. Okay? So that's any questions? Oh, Ruth is trying to get in. Okay, here we go. Let me get another. What I want to do, I want to start a new chapter. Okay, here you go. Here you go. Concepts of force and mass. Now we're going to start talking about force. Force is Newton's law of motion. Okay. Now we will talk about force. Force and Newton's laws and the laws of motion. Let's go back to our building blocks of physics, right? Now it's time to start talking about our first law of physics that you're going to be introduced to. Here we go. Okay, 3 more. Let's see, 4 more. 4 more. I told you about the primary definition, but that was the position, the force, but I still didn't start talking about force. Force is going to be introduced right now. And our first law of physics is going to come into this chapter as well. In the laws of motion, chapter 4. Okay. What's force? Force is a push or a pull. Okay. This idea of force has been around since antiquity, maybe even longer than that. Since antiquity. And it's a good idea. It helps us explain the universe in a rather reliable way. Contiguity. It is this is a triad and test. This is a triad and tested idea that has been around for a long time, and also very reliable. Okay, think about that. Have been using this idea for 4,000 years already. The idea of force for 4,000 of years. And force, is a vector. I push consequently, a push and a pull will have a direction and magnitude, right? Magnitude. And there are a few forces out there. There are a few forces out there that are very important, okay? The most important of them, let's see, there are all sorts of forces. Let's put it this way. There are all sorts of forces. And you have to memorize them. Okay? One of the forces, the first force that I want you to memorize, that you must memorize is the weight, or the force due to the force due to gravity. Okay, and I'm going to show here is, okay, here you go. Here's an object resting over a surface, okay? Let me see here. Let me draw this object here. So this object is resting over the surface, okay? The force of gravity is going to be always perpendicular. It's going to be always in the vertical direction, okay? The force of gravity. And this force we represent by m times g, where m is the mass of the object. Okay, remember, m is the mass of the object, which is a basic quantity, right? And g is the acceleration of gravity. The weight is also we can represent the weight by the letter W. Whether this block is in contact with the surface or not, this block still will be subjected to the force of gravity, okay? Whether it's in contact with the surface or not, it's still be subjected to the force of gravity. Just like this checkbook of mine or your cell phone, okay? Everything that has mass has a weight, okay? Every object that has mass, let's write that down here. Every object that has mass is also subjected to this force. The force of gravity or weight, the force of gravity or the weight. Force of gravity and weight are exactly synonyms. It means exactly the same thing, okay? So that's the first force that you have to memorize. There's more. There are contact forces and non-contact forces, okay? And very few, here you go, and very few non-contact forces. The weight is a non-contact force. But there are other non-contact forces, not just weight. There are very few. Okay, most forces are contact. Let's see, and most forces are contact forces, and very few are non-contact. Weight is just one of them. But then there are others. Okay, there is the magnetic force. Other examples of non-contact forces. Other examples of non-contact forces. Magnetic force. Electric force. Okay. And then we have the strong force at the nuclear. This is a nuclear force. This is a nuclear force. This is a nuclear force. And strong force and the weak force, okay? These last two forces are nuclear forces. Nuclear forces. The magnetic and electric force we will study in more detail in physics 7, okay? So let us stick to the gravitational force, which is given by, again, I want you to memorize that. It's not difficult to memorize. The weight is given by mg. You have to memorize that. Now let's talk about contact forces. Let us now talk about the contact forces. Okay. We have the force between surfaces. We call normal force. Normal force, okay? I have the force between surfaces, normal force. Let me illustrate here for you. My cell phone resting on the top of my book. Okay, my cell phone here resting on the top of the book is subjected both to the weight, but it's also subject to this contact force between the book and my cell phone. Okay, my book is preventing my cell phone from falling, from moving downwards. Okay, and this is a normal force. Here's an illustration of this force. You have already seen that. Here you go. The block, right? Resting over a surface. You have this weight, but you also have this normal force. This normal force prevents my object from keep on moving downwards. if you had the weight alone here, right? The object will be moving downwards. But because it is in contact with the surface is exerting a normal force that cancels out the weight. Okay, that's one normal force. But we can talk about another normal force. Suppose that this book is not only resting over a flat surface, but also is touching the wall, a vertical wall in your room. There will be another normal force in there, to the left in this case. And normal means just that, normal to the surface. Here you go. I'm going to write that down here. Normal forces. We have force between surfaces. The normal force, for instance. The normal force, for instance. Normal forces have a direction that is normal, okay? Or perpendicular to the tangent, to the tangential, to the tangent along the surface. Okay? Normal to the surface. Normal to the surface. Or you don't even have to put between parentheses, or perpendicular to the tangent along the surface, okay? And when I mean perpendicular to the tangent along the surface, I mean it, okay? When I say that. I'm going to give you an example of another normal force, okay? Instead having this flat surface, let's consider, for instance, a surface that's not flat, that's not horizontal. Consider a surface that is round, like that. And that's not good. I gotta get something better. Let's see, this one. Yeah. Okay. Here you go. Consider, a surface that's that has a curvature. Okay, a surface that has a curvature. And here you go. An object here at the very bottom of this curvature is going to be subjected to a normal force that's going to be exactly along the vertical direction, okay? Okay, here you go, normal force. We can put here N for normal. But if this object is elsewhere along this curved surface, now the normal forces will no longer be in the vertical direction. The normal force will be normal or perpendicular to the tangent of the surface. Did you get the idea? This one here is going to be, let's see, N1 subscript. And this other is going to be N2. Okay. Did you get the idea? And normal means perpendicular to the tangent of the surface. Here you go, the tangent to the surface is this one right in here. Let's see. I can get it, yeah. Okay, so this direction here is going to be perpendicular to this tangent. Okay. Now, here you go. Here's another normal force. This is my hand applying a force to the right. Okay, and it's going to be perpendicular to my hand. Okay, And here's an example of all the forces in a given object. An object resting over the surface, you will be subjected only to the normal and the weight. And what you see right in here is an example of free body diagram. Here's a free body diagram. Here's a free body diagram as well. Okay. Here's another free body diagram, which, by the way, must include the weight as well. Okay. Must include the weight as well. The weight is always perpendicular. Weight and weight. Okay. Free body diagram, very important. Okay, so normal forces can be vertical, horizontal, and make any angle with the can be vertical, horizontal, or make any angles with respect to a given direction. Whereas the weight is always vertical and pointing downwards. Okay. We have another type of force. Tension is another type of force. It is the force that a string applies to an object. Okay. Let me see if I have one here. Oh yeah, here you go. Here's my string, right? Right now, this string is not applying any force whatsoever to my block. But if I stretch the string, then now the string is applying a tension on this object. It can be, the tension can be at the horizontal, can be on the vertical, can be at an angle as well. Okay? So tension can be in any direction as well, just like the normal force. Just like the normal force, the tension can be in any direction. Okay. Which other force you should know? Here you go. There's another force that we call the force of friction. Force of friction. Okay. This type of force acts, has a direction, has a direction that is contrary to the velocity vector of an object. Okay. Contrary to the velocity vector of an object, or contrary to the tendency of the to the direction of motion. Here you go. Contrary to the tendency of motion of the object. It's better this way. Okay? Contrary to the tendency of motion of an object. If an object is at rest, right? Is at rest, it's not moving, but its tendency is to move to the left. If because there is some force, they're forcing it to go to the left, the force of friction is going to be to the right. Okay? And that's what this illustration is all about. Here you go. We have this tension here, pulling the object to the right, right? So there must be a force of friction, specifically the force of static friction, because the object is at rest. This force must be to the right, to the left. Okay? If an object is at rest, but has a tendency to move to the right because of another force, comma, the force of friction will point to the left, right? Similarly, here you go. If an object is moving to the right, comma, the force of friction will point to the left. Let's see if we need more forces. There's a bunch of forces out there, okay? But let's see, we have 1, 2, 3, 4 so far. I think we can stick to those for now. There are more, not just those, okay? So let's stick to those for now. Get used to this idea of force. When you see that for the first time, it's a little bit difficult to understand, but eventually after looking at it over and over again, you end up memorizing them, okay? It's very difficult, let's put this here. It is very difficult to grasp this idea of force if you see it for the first time. However, as you solve several problems, you will start memorizing them, okay? So, four types of forces so far. There are more, okay? Remember, there are more. The weight, the normal, the tension, and the force of friction. Okay? All those. Let me see if I'm missing. Oh man, that's it. Here you go. So there are some messages here. That's why VBA is negative, right? Let's see. I missed your question here, Sean. Can you did I already answer your question, Sean? That's why VBA is negative.
Yeah.
Yeah, I did. Okay, good. And now Jeremiah. Okay, Jeremiah missed the roll call. Let me give you attendance. Well, if I start talking too much and don't answer your question, that's because I didn't see your message. Okay, so feel free to come and talk in the mic. Jeremiah, and here you go. What about Elena? Are you there, Elena? Harry is trying to come in.
Here.
Okay, Elena's here. Thank you, Elena. Okay. And it's 11:05. Let's have our break. Notes. Not this one. I want the other. Break 11:05 to 11:20 a.m. Okay, so when we return, we will see the first law of physics, law of motion. Okay, so I see you in 15 minutes. And now I'm back here. Let's start sharing the screen. Okay, now we have enough forces here to play a little bit with that. And I'm going to, wait, right? Let's make a list of those forces. Weight, and that should be the first one that you have to have in mind. There's a little bit more about the force of friction that we're going to see later on as well. Here you go. Weight, normal, tension, and the force of friction. Let's play with those four for now, and as we go along, I will introduce more forces for you, okay? And now we are going to start looking at the first postulate of physics, the first law of physics, law of postulate. Remember, we haven't introduced that yet to you. That's because we need to have all that information, we need to study all those things about motion kinematics, especially acceleration, because acceleration is intimately connected with the concept of force, okay? And the first law of physics, I'm going to break it down into two parts. Okay, the first law of physics, also called first Newton law, Newton's law of motion. Law of motion. It's also called Newton's first law of motion. First law of motion. I will break down this law in two parts. Okay? For V at rest and V constant velocity different of zero. Okay? Two parts. Okay, first part. First part of first Newton's law. First part of first Newton's law. You have to memorize this statement. This is a statement, okay? If an object is at rest, V equal to 0, then the net force applied to this object is 0. Okay? Here you go, my book is at rest on the top of my hand. Consequently, the net force applied to this object, remember, it's the net force, not just a single force, but you can have multiple forces acting to this object. It means that the net force in this object is 0. Okay? However, keep in mind that the converse right? The converse is not necessarily However, keep in mind that the converse is not necessarily true. Is not necessarily true, okay? Keep that in mind. If an object is at rest, vehicle, then the net force applied to this object is 0. However, if the net force applied to an object is 0, it may not be at rest necessarily, okay? Very important. The reverse, right? The reverse is not necessarily true. And I'm going to give you some examples in those graphs in those illustrations that you have seen before. Okay, so here we go. I have my block at rest over the surface. It is at rest. I am indicating here that this object at rest. This is the information that's given to you. So the question that I may ask you is, what's the net force applied to this object? Okay? According to Newton's first law of motion, you respond the following, right? According to the first part of Newton's first law of motion, the net force must be 0, okay? And you started identifying the forces, right? Oh, here you go. The weight is always going to be there. The normal is going to be there because the object is in contact with the surface. And the free body diagram is going to be something like that. Okay? And let's not forget, you go V equal to 0. Here V is equal to 0, and here V is also equal to 0. If you don't think you're gonna have any more forces there, doesn't look like there's any other force, right? Because there's no string here being pulled. The object is not moving. There is no horizontal force. The object is not on the verge of motion. Consequently, there is no frictional force here. So in this specific case, okay, there are only two forces. Okay. Example, an object at rest on a surface. Okay. What is the value of the net force? Okay. Solution. According to the first part of Newton's first law, since the object is at rest, its net force must be 0. Okay. And I'm gonna make accordingly, there are only two forces applied to this object. Its weight and the normal force that the horizontal surface exerts on the object. This normal force is preventing the object from moving downwards, okay? Mathematically, we can also state the following. Mathematically, we can also state the following. Okay. The net force, which means the sum, net force means the sum of all forces, okay? The sum of all forces. I'm going to represent it in a different way. Here you go. Net force is the summation of all forces applied to the object. Here you go. Like that. Instead of net here, I'm going to put the subscript I. And the subscript I here is going to be the index of my summation, going from force number 1 until force number n. Since there are only two forces here, okay? Since there are only two forces here, I can write down that n is equal to 2, right? And let's say the force number 1 is going to be the normal, the force number 2 is going to be the weight. And here you go, equal to 0. Everything is going to be equal to 0. That's the vectorial equation that you have to keep in mind. Okay. Example 1, right? Let's see, let's get another example. Going back here. Okay, now we are introducing this wall here. That's applying this force, this horizontal force to the left, right? But the object is still at rest. But let's go for our free body diagram. Here you go. We have this horizontal force to the left because there must be another horizontal force to the right. Okay? Since the object is at rest, we must have also a vertical force to. Okay, I didn't put that. Let's put it here. We must have another vertical force downwards. And this vertical force downward is going to be the weight. The magnitude of the weight must be equal to the magnitude of N1. Otherwise, the object will be moving in the vertical direction, right? Here you go. Like that. Another example. Let's write it down here. Example 2. Example 2. At rest on a surface. On a horizontal surface. At rest on a horizontal surface. Touching, being compressed, okay, being compressed against a wall. What's the value of the net force? Okay, again, according to the first part of Newton's law, since the object is at rest, its net force must be 0. Accordingly, in this example, we now have 4 forces. 4 forces. Its weight, comma, its weight, its normal, the normal in the vertical direction, okay? Another normal in the horizontal direction due to the wall, right? And the force that your hand is applying in the object. Okay. I think I'm going to draw it slightly different, this one here. Okay, so here you go. Let's see. I'm going to draw it slightly different. Okay, instead of doing something like that, okay, I'm going to do different, okay? We identify the first force. The object is not moving in the vertical direction, right? If the object is not moving the vertical direction, it means that we must have a weight being applied to this object. But if we apply another force in the horizontal direction, like my hand here, right? If I don't draw, if I apply another force to this object, another normal force to the right, since the object is at rest, we must have a force to the left. Did you get the idea? Okay, I must first tell you that I am compressing the object against the wall, and only then we can deduce that that must be another normal force being applied here. And now I can get rid of this, okay? Those forces. I'm going to rename that to N2. I'm going to rename that to N3. Yep, N2 here. N1, N2. N2 again. And this one is going to be N3. I thought I had corrected that, right? Let's see here. Here you go, wall, N1, weight, N2, I'm compressing the object, and N3. I don't need that. Okay, like that. Going back here to my notes, right? According to the first part of Newton's first law, since the object is at rest, its net force must be 0. Accordingly, in this example, we now have 4 forces applied to the object. This weight, the normal in the vertical direction, another normal in the horizontal direction due to the wall. The force, let's say, that your hand is applying to the object, let's put here. The force that your hand is applying to the object, and another normal in the horizontal direction due to the wall. We go. Here is going to be our equation for the net force. The net force, we have 4 forces, so N is going to be equal to 4, right? F2, F3 plus F4 equal F3 plus F4. My F1 is going to be my normal 1. The second force is going to be the weight. The third force is going to be the normal 2. And the last force is going to be the normal 3 equal to 0. Okay? Let's see if you have another example. Free body diagram. I'm going to get rid of that. I don't need that anymore. Now we are going to have the similar situation, okay? But now we're going to talk about the tension force. Okay, and I need to write down here that V is equal to 0. V equal to 0. V equal to 0. V equal to 0. V equal to 0. Force of friction. Okay. Another example. Oh, did I do something here? Oh man, not supposed to do that. Here you go. Almost deleted everything. Examples. So let's write it down. Any questions so far? Am I missing any question from you? Oh yeah, 2 questions here. Is N3 there to counter N2? Yeah, let's see. In this case, yes, because they are horizontal forces, right? They are horizontal forces. Okay? But N1 is not countering N2 nor N3, okay? Because they are vertical. They're vertical, perpendicular. Who is countering N1, Molly? Which force is countering N1 in this case?
W.
W, yeah, the weight. Okay? N1 cannot counter N3 because it's perpendicular, right? The projection of N1 along the N3 force is going to be 0. Okay, the weight is not countering N3 and N2 because it's perpendicular to both of the forces. Okay? So here you go for normal force, here you go. String. So now we're going to do another example. V at rest. The object is at rest. Okay, and we need to separate that so we can get it. This one is going to be a little bit more difficult, okay? If it's a force like that in the horizontal direction, you know, it would be easier than this force here in the vertical direction. So let's do this one first, the force in the horizontal direction first, and then we do the force with this component, okay? One, and then I have to do the following like that, and I'm going to do it like that. Okay, here you go. String. I apply tension to the string. And if the object is at rest, there must be another force to the left. Okay? And this force to the left, it would be the force of friction. The force of static friction. Even better. I call it the force of static friction. That's why I put that S there. If you have the force of static friction, that's because you have another force, which is going to be force of kinetic friction. Oh yeah, I have to do something else here. Nope. You go. What do I have to do? I have to get this force here of static friction and place it right in here. This one belongs to the other one. Okay? V equal to 0. Another example. Example 3. Here you go. An object is at rest on the horizontal surface and being pulled, pulled, that's right, being pulled by a string of tension T, okay? What's the value of the net force, right? According to the first part of Newton's first law, in the object that right, its net force must be 0. Okay, and now I'm going to do it slightly different, okay? We're gonna do like that. Here you go. Net force is 0. Accordingly, in this example, we have, here you go, we have 4 forces applied to this object. Its weight, it's normal, the tension in the string, and the force of friction. Even better, I'm going to force of static friction. It is static friction. It is static friction because the object is at rest, okay? The summation of all these forces is represented by the following vectorial equation. Vectorial equation. Go. For F1, F2, F3, F4, but now F1 is going to be N1, weight, right? Do I have N1 there? Let's see if you have N1 there. Now I put N, so let's write as N. Yeah. Like that. What else do we have here? We have the tension, right? That I mentioned to you. Here you go. And then we have the force of static friction, F sub S. That's going to be equal to 0. See, now we have a vectorial equation here. And this vectorial equation has two components. Consequently, although I have just one vectorial equation, I end up having two equations, two scalar equations. I'm going to break down in, here you go. X component, right, of this equation. The X component are going to be the tension. Oops. I'm going to denote the tension like that. Magnitude of the tension. I'm going to make it a little bit more challenging here, right? In the positive X direction, right? And then I'm going to have the magnitude of the force of the static friction. But wait a minute. Oops. Oh, I didn't get there yet. Let's see. No. Here you go. I'm going to get this force of static friction put inside this magnitude sign. There will also be an X direction. But if you look at the drawing, it's going to be a negative X direction, right? Because it's to the left. Positive is to the right, negative is to the left, right? So I'm going to write that down here. I'm going to put it between parentheses. Negative direction. Okay? X component. That's how we solve those problems. All you have to do next is just to plug in the numbers. If I give you actual numbers, okay? X component, and then we repeat for the Y component. Y component. Okay, the Y component, let's see, the Y component is going to be normal. This normal component is going to be along the positive Y direction, okay? And then we are going to have the weight. It's going to be along the negative Y direction. We go. And those reduces to a scalar equation. I didn't do that, right? The scalar equation. The scalar equation for the first one looks just like that. You put the X hat in evidence, just like we are doing. Right? We put the X hat in evidence. Right? And this vectorial equation reduces to a scalar equation. Scalar equation that's easier to solve. And I can even go another step. Very soon I'm going to go another step. And the next step is to relate the tension with the force of static friction. They're not going to be 0. They're going to be equal to each other. And we can do exactly the same thing with the weight and the normal. Okay, this one, this one. We're gonna put now them in evidence. All right, here you go. Put the y hat in evidence. And then this vectorial equation turns into a scalar equation, just like we did before. Y hat is not equal to 0. Consequently, we can state that its a scalar component is 0. And the last step is going to be the normal must be equal to the weight. Like that. 11:52, we're running out of time. Let's see, this is example 3, right? Now we're going to do example 4. That's a little bit more difficult. A little bit more difficult, right? Example 4. Okay, good. So we got it here. Example 4. An object is at rest on a horizontal surface and being pulled by a string of tension T, making an angle theta with the horizontal. What's the value of the net force? Then I'm going to ask more questions here. You know, I should have been doing that. Here you go. 1. I. What's the value of the net force? 2. What is the relation between these vectorial forces? No, even better. Let's see. Let's do it this way. How many forces are being applied to the object, right? Like some object, you know? I. What is the relation? What is the vectorial relation between these forces? That's what we did in the previous 3 examples, right? These forces. 4, right? Right down reduces you write your vectorial equation into scalar equations. Okay, you write your vectorial equation into 2 scalar equations. Okay, so the first part is always going to be 0 because it's at rest. The object is at rest, right? Accordingly, in this example, we have 4 forces applied to this object. Its weight is normal. The tension in the string and the force of static friction. It's called static friction because the object is at rest. The summation of all these forces is represented by the following vectorial equation. Okay? Normal weight tension is exactly the same. Okay? How many forces? This one, I, right? I. There are 4 forces. The weight, the normal, the tension, and the force of static friction. Now we gotta go third part. 1, 2, 3, right? What's the vectorial relation between these forces? Okay, I'm writing down the vectorial relation between them. The vectorial relation is this one right in here. Okay, and now we're going to break it down into the 2 scalar equations. for X component, right? Now X component is going to be a little bit different. The X component is going to be a little bit different because you have to break down your tension into horizontal and vertical components. See that? There's an angle of theta right in here. Let's write that down here. Here you go. Oops. This one. Yeah. Right in there you go. And I'm going to denote the horizontal direction here as a dashed line. Dashed line, here you go. Here you go. T for tension, and I'm going to place it right in here. And I also going to denote the angle theta. We start with the letter Q and change the font to symbol. Okay. Theta is not equal to 0, so I gotta erase that. Now the tension has two components, the horizontal component and the vertical component. See that? So my X component here of the tension has to be written as a cosine of theta. Here you go. Right? And I repeat T cosine of theta. Right? I repeat here T cosine of theta. And then we have T cosine of theta here. The scalar equation, right? Here's the vectorial equation, here's the scalar equation. And then we have this relationship between T, theta, and the force of static friction. For the Y component, okay, let's take a look for the Y component. For the Y component, we are going to have the normal, we are going to have the weight, and then we are going to have this Y component of the tension, right? The Y component of the tension is pointing upwards. Consequently, it has a positive sign. So here you go. Now, I'm going to copy this one, and it should be a positive sign instead of cosine. It's going to be a sine, and we still have our Y hat. Did you get the idea? This one is slightly more complicated than the other. And then we keep on writing, right? We keep on writing, right in here. It's still a vectorial equation. And now, since Y hat is different of 0, so this scalar term that must be equal to 0, right? So here, like that. Can you do better than that? Well, maybe, something like that. Okay? Those two components must be equal to the weight. Okay, what time is that? 12 noon already. Okay, so we did 4 different examples. Okay, involving the normal, the weight, the tension, and the force of static friction. 4 different examples. And that's still the first part of Newton's first law. Okay, next time we're going to get into the next time. We will get into the second part of Newton's first law. Okay? Any questions? Is N3 there to counter N2? Oh, yeah, I already answered that, right? Do you have any questions? You don't have any questions, so there is office hours right now. You can stay around. Okay, and I will, if you If you don't stay around, then I'll see you on Wednesday. Don't forget the lab report, right? The first lab report. Don't forget that. I can give you another 2 days to turn in the lab report, okay? So I see you on first lab report. You can turn it in the day after tomorrow, okay? 2 more days, the day after tomorrow. 2 more days. 2 more days to turn it in. Okay?
Do we need to upload it to Camino or should it just be in our group folder?
In your group folder.
Okay, thank you.
You're talking about the spreadsheet, right?
Yes,
Yeah. Upload to your group folder. Yeah.
thank you.
Okay.
Professor, is the spreadsheet the only thing that's due for the lab report or do we need to write something up?
Yeah, that's right. Yeah, just the spreadsheet, nothing else.
Okay,
Okay.
perfect. Thank you.
Okay, see you.
See you Wednesday.
See you.
Thank you, Professor.
Welcome. Yeah, Danae, are you there? Okay, so you wanna check what you missed in the exam?